So the official welcome, super excited to welcome you at the first Serverless Tribe webinar. So Serverless Singapore became Serverless Tribe during the summer. And as part of that change, it went global, which means that it's going to be online. It's going to have participants from all over. And I'm pleased to welcome Shirley and Sagar as the first guest of the webinar. Welcome, and thank you for being with us today. So Shirley is a committer from Apache Doris community, and she will have her presentation first. And Sagar is a database engineer at Onehouse and Apache Hudi committer. Welcome again. And perhaps Shirley can take the floor first.
Yes, thank you for the kind introduction. And let me just share my screen. So here it is. So this is my talk today. I will give you an overview of Apache Doris. And I assume some of you might have heard of it to various extent, but this is the very first time that we bring Doris to you in a comprehensive and structured way. And a little bit about myself, and as it's mentioned, I am from the Apache Doris developer community. I'm a committer, and I also work in developer relations at SelectDB. And I will talk about what Doris is, what it does, so you have another option to think about when solving your data problems. So Apache Doris is an open source real-time data warehouse. And as an open source project, it just graduated from the Apache incubator last year, but it has actually gone through 10 years of development. And so far, it has a user base of over 2,500 enterprises. And we have a busy release schedule. And recently, just last month, we released our version 2.0, which is kind of a breakthrough for us because it has a lot of great features, and I will talk about them later. And the Doris community is fast growing. It is now one of the world's biggest open source project in the data area by the number of monthly active contributors. So what Doris does in the data pipeline is it collects data from various data sources, like the relational databases, the big names, MySQL, Postgres-SQL, SQL Server, and Oracle. It can also collect your logs, your time series data from your IoT devices. And then when you have this data in Doris, you can generate reports, you can do ad hoc analysis, federated queries, and the like. So on the application side, you can use Doris to support your dashboarding. You can build your self-service BI platform. You can analyze your sales, orders, and user behaviors. And of course, when it comes to data ingestion, you might need some extra tools. And Doris can be well integrated with Spark, Hive, Flink, Airbyte, DBT, and Fivetran. And it can also be connected to data lakes such as Hive, Hudi, Iceberg Delta Lake, and the newly emerged Apache Pymon. And when we talk about real-time databases or real-time tools, the first thing that people look into is speed, right? So for your reference, these are the TPCH benchmarking results of Doris against some of the great products on the market, Presto, Greenplum, and ClickHouse. And as it shows, Doris has a competitive edge. It can respond to all these queries in a much shorter time. And we know some of these tools are better at flat table processing, but Doris is also competent in SSB benchmarks. So these are the comparisons against other products. And as for Doris itself, it has been actively evolving during the past 2 years. It has increased its performance by over 10 times compared to its early versions, and both in complex queries and flat table queries. And of course, all these tests are done in the same environment, and you can refer to the setup here. And this is a peek into the speed of Doris, and it looks promising, but after all, it will be slightly different for every use case. So what's more important than the benchmarking results is the design and features of the tool that enable it. So in the next part, I'm going to introduce to you the architectural design and a few features and mechanisms that contribute to the high performance of Doris. First of all, Doris has a cost-based query optimizer. It can figure out the most efficient execution plan for the complicated big queries. And it has a fully vectorized execution engine that can reduce virtual function calls and cache miss. And it's MPP-based, that means it's good at parallelism, so it can give full play to your machines and cores. And then in Doris, query execution is data-driven, which means whether a query gets executed is determined by whether its relevant data is ready. So that can enable more efficient use of CPUs. And these are the efforts we made in architecture and orchestration. And besides these, Doris has a few other ways to speed up the queries, including a rich collection of indexes, and it also has materialized fields and a comprehensive caching mechanism. So in essence, Doris is a column-oriented database. What's good about that is that it can make data compression and data sharding easier. But in some cases, for example, when you need to provide customer-facing services with your data platform, you will have many users requesting data from your system at the same time. But each user only asks for a small piece of data, like 1 or 2 rows. And these are what we call high concurrency point queries. And in these cases, especially when your data is arranged in flat tables, having a columnar storage engine will amplify your I/O operations per second. So to fix that, we have enabled hybrid storage, which means you can have both row storage and columnar storage at the same time. And also for these queries, especially since they are simple queries, it will be unnecessary and kind of wasteful to call out the query planner. So Doris executes a short circuit plan for these queries to reduce overhead. And another big source of overheads in these cases is SQL parsing. For that, we have prepared statement. The idea is to pre-compute the SQL statement and then cache them. So when you have many similar queries, you can just reuse these statements in the cache. And next, I'm going to follow the data flow and show you how you can use Doris. The first step is data ingestion, of course. And Doris provides a wide range of methods for you to choose from. Like for real-time streaming, you can use Streamload, which is a way to write local files or data streams. And this method is linearly scalable. And in some of our use cases, this can reach a throughput of 10 million records per second. And then we have the Flink Doris connector. It is what we built to ingest data from OLTP databases to Doris. And as the name implies, it has built-in Flink CDC, And so far, we have realized auto-synchronization of data from MySQL and Oracle to Doris. And if you're a user of Apache Kafka, you might want to know about routine load, which is to subscribe data from Kafka message queues. And if you try to do ETL in Doris internally, which means you want to write data from one Doris table to another, you can try insert into, which if you are familiar with MySQL, you should have no frictions with. And then for batch writing, we have Spark load and broker load, which are the ways to write data from HDFS and object storage to Doris. And with Spark load, you can leverage the Spark resources to pre-compute the data before you write it to Doris. And if you try to build a data lakehouse, you can apply this simple statement called insert into internal table, select from external table. It is how you connect Doris to different storage systems, data lakes, and databases. And we've also been expanding our ecosystem. So besides the Flink connector, we also have Spark connector. And currently we are working on a data migration tool called X to Doris. And it will have a visual interface, so it's going to be very user-friendly. And we are also working on the parallel load and read-write separation, which will be available with our next release. And now with your data already loaded in Doris, the next thing you do is to keep your data updated, right? And if you look around the database world, you'll find that most data updating mechanisms are just not designed for real-time analytics. Like some of them update on the data partition level, which is not fine-grained enough. And some of them implement merge on read or copy on write, which is still not suitable for frequent updating. And of course, transaction processing systems are good at real-time updating, but they are short on analytic capabilities. So what Doris has to offer is that it supports both merge on read and merge on write. And the former is for low-frequency batch updates, and the latter is for real-time writing. And the merge on write mechanism will improve your query speed by 5 to 10 times compared to merge on read. And then from an implementation perspective, data updates can be divided into a few types. And a common one among them is upsert, which usually means you replace or update a whole row. And we also have partial column updates, and that means to update just a few columns in a row. And sometimes you have to do conditional updating, which means you filter out some data by combining a few conditions, and then you update or just replace and delete them. And sometimes you also need to replace a whole table or a whole data partition. And these are the common updating operations, and Doris supports them all. And also in some cases, data updates will just happen concurrently. And that means you have many new data flowing in, trying to modify your existing one. And in these cases, the order of updating will matter a lot. So that's why Doris allows you to decide the updating order. You can say, let's follow the order of transaction commit, or let's follow the order of the sequence column, which is something that you specify in your table in advance. And so far, we've been talking about speed, either the speed in queries or the speed in data ingestion. But Doris also pays attention to service availability. And architecturally, Doris has two processes, which are front-end and back-end, as this figure shows. The front-end nodes manage the metadata, and the back-end nodes execute the queries. and they can do auto data balancing and auto restoration. And both the front end and back end processes are scalable. And when you need to upgrade or scale your clusters, you don't need to stop the whole system. And so you can avoid interruptions to your services and business. And then for data reliability, Doris supports snapshot backup and snapshot restoration, both at the table level and at the partition level. Now, for enterprise users, especially those in finance or e-commerce, they would need to back up their clusters or even their entire data center, just in case of force majeure. So in Doris 2.0, we have CCR, which is cross-cluster replication. And these are what you can do with CCR. Like I mentioned, you can do disaster recovery, and it also allows you to separate your read and write operations, because you can then have one master cluster and one slave cluster. So you have one cluster for reading and one for writing. And when you need to upgrade your clusters, it allows you to pre-create a backup cluster. So we can run things on the backup cluster for tests or to clear out any incompatibility issues or any bugs you may encounter. So how does Doris CCR perform? And in our tests, it's able to reach a data latency of minutes. And if everything goes well, your data synchronization speed will only be limited by your hardware. And then we come to multi-tenant management. Doris has sophisticated role-based access control. It allows fine-grained privilege control, like on the level of database, tables, rows, and columns. And then for resource isolation, in these cases, Doris used to implement a hard isolation plan, which is to divide the backend nodes into resource groups and assign the resource groups to different workloads. It was simple and neat, but one problem is that you don't make the most out of your resources, because sometimes some resource groups are just idle. So we have improved on that. And instead of resource group, we now have workload group. And we set a soft limit for a workload group about how much resource it can use. And when that soft limit is hit, and meanwhile you have some idle resources in your system, those idle resources will be shared across the workloads to share the burden. And you can also prioritize the workload groups to say which one can get more resource and which less. Now, if you worry about would Doris be hard to grasp or difficult to get started with, let's just say that Doris is compatible with MySQL protocol, and it supports standard SQL, and it can be connected to most BI tools on the market. And this is another feature I would like to talk about. It's called flight schema change. This means if you need to add or delete some columns of your table, you can just update the metadata in the front end, which is quick and simple, but you don't have to modify all your data files. And this can be done within milliseconds. And it also allows you to do other changes, like to the indexes or to the data types of columns. And if you use this feature in combination with the Flink Doris connector, as I mentioned, you will be able to synchronize your data to the upstream tables in milliseconds too. And these are the efforts we made in expanding the capabilities of Doris. And speaking of this, you would think of logs, you would think of observability data, security data, and time series data. And in these cases, people are looking for schema-free support. People are looking for lower costs and capabilities in multi-dimensional analysis and full-text search. So Doris makes optimizations to support them. Like in text analysis, mostly people use an operator, which is the like operator. So we put a lot of effort to improve the performance of that. For example, we introduced the n-gram Bloom filter, and we also push the like operator down to the storage layer so we can reduce the amount of data scanning as much as possible. And then we have also introduced inverted index for text tokenization and full text search. And the inverted index is a powerful tool for fuzzy keyword search and equivalence queries and range queries. And then to fit in with more data structures, we have compound data types. Like besides array, map, and JSON, we are now working on the variant type, which means you can put various data types into one field, and it's going to be available in our next version too. And of course, we have also made some improvements in storage and writing accordingly. And if you want a faster data lakehouse, or if you want to build a unified query gateway, you can look to Doris too, because it can map, cache, and auto-refresh the metadata from external sources. It supports Hive Metastore and almost all open data lakehouse formats. You can connect it to relational databases, Elasticsearch, and many other sources. And it allows you to reuse your own authentication system on the external tables, like reuse what you have in Kerberos and Apache Ranger. And then with all this done, we have benchmarked Apache Doris against Trino to see how it works. So it turns out that Doris is 3 to 5 times faster than Trino in queries on Hive tables. And how do we do that? It is the joint result of a few features. And first of all, the Doris query engine is efficient. It can cache the hot data locally. And we have a special solution called compute nodes. And these are different from what we usually have as backend nodes. These nodes are stateless and they do not store any data. So during computation peak times, these compute nodes can flexibly join the clusters to share the computation burden. And lastly, Doris allows you to write the computation results of external tables into Doris to form a view. And this is a similar thinking to materialized fields. So when you execute a query on the external tables, you can put the results in Doris internally. And then when you have similar queries following up, you can just directly read the previous results from Doris, and that makes things faster. And then this is another big job we've done in the new version 2.0. We have enabled tiered storage, and the main purpose of that is to save money for you, because it allows you to put your hot data in the quick but expensive disks, and then your cold data in object storage, which is more cost efficient. And with hot data, we mean the data that you frequently access, and cold data that you don't. So roughly speaking, if 80% of your data asset is cold data and you put it all in object storage, you will be able to reduce your storage costs by around 70%. And this number is calculated based on the AWS pricing for S3 and HDD and SSD. So number may be different in your case, but generally this is a big money saver. So this is it. This is what I find amazing about Doris, which again, it's an open source real-time data warehouse. And if you have any questions about this talk or you want to know more about any aspects of Doris, these are where you can find us. And I strongly recommend you to join us on Slack because you'll be able to directly talk to our developers and many users. And of course, you can also come to me. And this is my personal email, and I will provide the tech details or introduce you to the right person for that. So thank you again. It's really nice to meet you guys here.
Many thanks, Shirley. I enjoyed so much. I hope everybody else did. Just a quick reminder for people who join us later, this will be recorded, so you can get the recordings. And I was just wondering before Sagar starts his presentation, is there some questions that you want Shirley to address now? You can use Q&A. There is a Q&A button, so feel free to use it, like ask your questions. And maybe like if you don't have questions now, we can like collect all the questions at the end after Sagar's presentation. Okay, Sagar, welcome, your turn. And you're muted.
Thank you. Thanks, Shirley, for the great presentation. It was. I do have a few questions. I'll queue it up in Q&A. So let me begin with my presentation. All right. So I'm going to be talking about how we can build a scalable real-time CDC streaming pipeline using Flink and Hudi, and query that interactively with Presto. And a little bit intro about myself. I'm Sagar, the database engineer at Onehouse, and I have previously worked on distributed data systems at AWS and Oracle. I'm also an Apache Hudi committer, actively contributing to the project, and we'll talk about Hudi design as well in this talk. So let's first start by, I want to open the discussion by talking about challenges when we want to do CDC streams on data lakes. A lot of these things are simplified in Warehouse, but Warehouse have their own challenges and cost concerns. And there is an emerging paradigm, emerging data platform architecture called Lakehouse, which many companies are moving towards. So we start by describing the challenges of streaming data set on data lakes. And then we'll discuss about what Lakehouse architecture is about. We'll discuss about the solutions to those challenges using Hudi and Flink integration. And then we'll look at how to do adhoc querying with Presto for Hudi tables. And then if time remains, I can go through a demo of this whole end-to-end setup. If not, then I have a recording for the demo as well as the code that was used to produce it. So you can look at it at your own time. I hope this slide deck will be shared with the community. Yeah. All right. So let's start by the challenges first. So what's the first challenge? So first thing is ingestion, right? Everything starts at ingestion. And there is a trade-off with ingestion that you can very quickly, very fast, do a very fast ingestion if you directly write files to the storage in append-only mode. But you could end up with a huge log of numerous small files. And over a period of time, it will be clear to you that not only does it affect your ingestion, but also the queries side. When you're querying your data, it needs to scan so many files. So can we do something like automatic small file handling while writing on the fly? We'll look at how Hudi achieves that. So that's the first challenge. And then the next thing is, fine, you are ingesting, but you want to be uh, the changelog materialization itself. How do you do that? Especially when it's a CDC stream. It's not, you're not ingesting the CDC events as a batch. It's stream by nature. It's unbounded. And Flink, as we all know, it's a beautiful piece of streaming system software, and recently it won the Sigmod uh, award as well. Um, so Flink definitely has some strengths, and that's why we Hudi Flink integration makes use of this dynamic table in Flink. But there are some drawbacks with dynamic tables. First, this dynamic table is not queryable in the sense that it's essentially a stream. It's not a table that you can query through other engines, uh, such as Presto or Trino. And second, the dynamic table cannot be shared among multiple jobs. And this becomes challenging when you have joins involved in between. Then your computation costs become quite high. And the third thing is that there is no history of snapshots for the dynamic table, and it's for a reason. It was not made for that use case. But due to these three challenges, we cannot directly use dynamic table for materialization. And tangential to the third point, that since you do not have history of snapshots, you cannot support features such as schema evolution as well. So we'll look at how that part is solved. Uh, the third challenge, so first thing we talked about ingestion, second we talked about materialization. The third is how to build an incremental pipeline. And what do I mean by that? One of the most common standard data platform architectures is the medallion architecture, where you ingest your raw data in bronze layer. Uh, it's just immutable data. You're just dumping events there. And then you build a silver layer off of that bronze layer with some maybe transformation in between. And then there is the gold layer data, based on which typically you are preparing dashboards or running BI queries. So this medallion architecture, there are some challenges with doing it in streaming style. And the thing is, uh, it needs to meet certain preconditions. So first of all, it needs to preserve that event sequence. Otherwise, there could be some correctness issue. Both reader, writer job need to have exactly one semantics. Um, and secondly, the reader also needs some way of bookkeeping, what it has consumed so far, so that it can easily recover without much overhead. So these three challenges, right? Ingestion, materialization, and incremental ETL. We'll look at how Hudi Flink integration helps in solving those. And before that, now I want to talk about the lakehouse architecture and Hudi design, which will help us in understanding those solutions. So what is a lakehouse? uh, in a very, very, very high level manner, we can just think of a transactional, serverless transactional layer directly sitting on top of your lakes. So it's just a bunch of metadata, some transaction logs, and some caching and indexing that helps to support the asset guarantees that you usually get with databases or data warehouse. You get directly on top of lakes, right? And Hudi was kind of pioneer in this when Uber was at hyper growth phase. They were ingesting huge amounts of data, but only few hundred gigs of data being updated out of hundreds of terabytes or single digit petabytes data. The rewrite computation overhead was a lot. And in order to eliminate that, that's how Hudi was born. That was the motivation. And incremental ETL is a first class citizen in Hudi. CDC and incremental ETL, right from the get go, we have prioritized this. The design is meant for that, as we'll see. So this is a diagram from the Lakehouse paper from Databricks, which summarizes the evolution of the data platform architectures, how we arrived here. Where, we essentially started with single tier data platforms, all structured data going into warehouses. Then there was two-tier architectures where for BI or analytics use cases, you did one thing, loaded data into warehouse and generated reports out of that. And for data science machine learning use cases, you did something else. Um, and all your data, structured, semi-structured, unstructured data, was being dumped into the data lake. But then the growing pains of data lake, the reliability issues, data management issues, and data, they kept growing up. And then this lakehouse architecture came up, where you have this very thin metadata layer, indexing layer, which helps manage all of this underneath, and it can help you serve all both the unique use cases directly on top of lakes. Um, and yeah, it unifies your both uh, the use cases, and at the same time it guarantees certain performance by optimizing the storage layout, and through indexes the ability to locate the records efficiently. um, so incremental ETL, what we mean by that is, as the name suggests, you are able to, if somehow you are just able to get what changed between two commits, uh, and apply those changes further downstream, that's all, incremental ETL. And this is not something which is very new, but doing it on directly on data lakes, especially when your data is spread across clouds, it's challenging. I, and these days nobody is running. I mean, I shouldn't say nobody. There are still big users of HDFS clusters, but everything, the trend is moving towards cloud, right? Heavily towards cloud, and the file system guarantees that you get from HDFS, those are not really available on cloud storage. So there are certain challenges due to that. So let's see how Hudi, what happens inside, how Hudi lays out the data. So one of the couple of core concepts here is timeline, Hudi timeline, and then Hudi file groups. So what are file groups? So the way Hudi ingestion works is, the way it writes the data is, it will go ahead and write data to some file, which will call base file, like the first version of that file, and then log updates to the log files. The base files are columnar. The log files today, they are row oriented, but we have plans of supporting both columnar as well. Um, so and then Hudi will merge this base file in the background. Compaction can happen and merge this base file and log files to produce another version of the base file with the updated data. Um, so the important thing here is that as you receive updates um, for a particular record, uh, Hudi will route that update to a log file belonging to the same file group. So Hudi has this powerful invariant, and that's why while you create your Hudi tables, it asks you to think a little bit about what's your primary key for the table. So one key and this file group has one-to-one mapping. Even for newer versions of this key, um, the file group will still remain the same. Within the file group, there can be multiple file slices representing each version of the data, right? So that's the first half of this diagram. Um, uh, but let's quickly talk about the advantages of this file layout. So from the point of view of writing to the table, if you have let's say multiple table services such as compaction or clustering running in the background, then the services don't block each other or the ingestion. Because of the log structured storage, we can easily offer the multi-version concurrency control and snapshot isolation, not just between readers and writer, but between single writer, ingestion writer, and this compaction table service. Um, and secondly, from the point of view of querying, the file layout kind of facilitates that you can query the data, uh, view the view not just the latest snapshot of data, but any snapshot at a particular point in time, provided you haven't cleaned the older versions. So that was about the top half of the diagram. On the bottom half, what you see here is that when a record gets written into a file group, Hudi's timeline also gets updated with what commit action is done. So this timeline, think of the timeline as an event log of all the things that have happened on your table. Uh, uh, an update happened, it will get logged into the timeline. Compaction happened, it will get logged to the timeline. So there are different commit actions, and even when a rollback happens, that gets logged into the timeline. So Hudi timeline, one important point to note that Hudi timeline has timestamp associated with each and every action. Um, and that kind of helps us in providing this temporal logic based on which we can do conflict resolution whenever we have multiple compaction and ingestion happening simultaneously. We are able to resolve conflicts if there is some file group where you are receiving the updates. And then from the timeline, the other thing that you see there is the metadata table. Metadata table is a bit different from the timeline. It's actually an internal Hudi table itself. So it's a Hudi table within the data table itself. And each partition in the metadata table stores information about the metadata of the files. And for example, there is one partition called column stats, which will store information about column min max, null counts, and so on. Then there is another partition called files, which will store about the storage partition, what all files are located within a particular storage partition. Another partition is Bloom filter index, where it will simply store the information about a record key is present in a particular file group or not. So this metadata table serves as a central place. You can think of it like an index. It serves as a central place where both writers and readers can query. On the writer side, when you receive updates, the writers can figure out, okay, this particular key, what's the location for the file where it is located, right? If we have to go by Bloom filter in Parquet, then essentially we'll have to pull the Parquet files and then scan those Bloom filters. So why not extract that information into a separate index? So that's the idea behind the metadata table, and we'll see how it's used in the query side. So this the file layout, to make it more concrete what those file groups and file slices are. I have put this slide. Actually, it's much better to explain for merge on read table. Copy on write table, it's even easier than this. So let's say at commit time 0, you had written to 3 file groups, file 1, 2, 3. They did not have any log files. So the latest file slice for this at commit time 0 are these 3 Parquet files. Now at commit time 1, you received some update to record A, updated to A prime, and D updated to D prime. So through index lookup, Hudi will figure out, okay, file 1 is the file group holding record A. It will create a log file under the same file group. So file 1, let's assume it to be the ID of that file group. And then similarly, it will create a log file for the file 2. Then at commit time 2, you receive another update where A prime gets updated to A double prime, E gets updated to E prime, and there is a new record inserted. So what Hudi is going to do is it will produce another log file within the same file group, file 1, for record A. And now there are 2 file slices within this file group. The latest file slice is the base file, and then your the log file containing a double prime. Point to note here is that log files are append only. So these data blocks get appended. You won't lose the A prime. Uh, and that's how we can do time travel as well. Suppose you wanted to look at the snapshot that was available at commit time 1. Hudi can easily tell, it builds the file system view APIs based on this layout, and those APIs can easily tell you what was the snapshot at that particular point in time. As I've written here, if you do a snapshot query, what you see. If you do incremental query, what do you see? And then let's say you did a compaction at commit time 3. What it will do is it will merge the file slice, base file and log files, to produce a new base file, and which will eventually have the merged records. The advantage of compaction, as you can see, is that now when a query comes in, it just needs to scan these base files. This has all the updated records. Had it not been compacted, the queries would have to do merge right on the reading time, and hence the name merge on read. But compaction is an async background process, and users can configure at a certain frequency how to do compaction. Um, so zooming out a little bit, this is a diagram from one of my favorite papers when I was at the university 10, 12 years back. There's a paper by Hellerstein, Stonebreaker, and Hamilton discussing kind of survey paper on architectural database system. And it still is one of my favorite papers. I revisit it from time to time uh, to ground myself, on what all is happening right now. Vector databases are all the rage, but at the base of it, sure, there will be some nuances specific to handling with vectors, but then the fundamentals don't change much. So I'll show you in the next diagram. So Hudi kind of sits at this transactional and storage manager layer, and it does that really well. And it is compute or engine agnostic. So for querying, you can use any of these query engines such as Presto, Trino, Spark, Hive. And we'll talk about the query section when we come there. So this is what a lakehouse platform using Hudi looks like. Everything starts with the lake storage, and then you have open file formats sitting there. Uh, so we like to call it a thin transactional database layer. Uh, Essentially, this is Hudi. You get the table format, which stores all this as schema and uh, anything related to build the catalog of that data. But then it's not just a table format. There are other things that Hudi will do for you in the background. It will run table services where you can clean older data or compact base and log files. It can cluster your data, sort your data by a particular sort key. It will index concurrently, and it has concurrency control mechanisms supporting both MVCC and OCC with lock providers. It has its own lock manager, which does this orchestration. And the community is working towards building a separate lake cache, which will kind of help. So while doing writing, you are still doing an index lookup, which requires at least one file IO, depending on how big your metadata is. Can we avoid that somehow? And then there is a meta server. So all these table services, can we extract it out to a separate server component, which will not only so meta server. Today we already have timeline meta server. You can serve the timeline directly through a server, a remote server, or it can be local to your embedded within the driver process. And we are trying to build more things around this, incorporate table services there as well. And then on the top, you have execution or runtimes, essentially the engines that you can use to query your data. So that was all the background about Hudi and some nitty-gritties about the design, which will now make the rest of the slides seem pretty easy. So we talked about three challenges, right? One was the ingestion, then materialization with dynamic tables, and then incremental ETL. So let's see one by one. Ingestion, the main challenge was that you could get numerous small files, and soon your storage will grow, which will affect your write path, read path, and everything will turn bad. So what does Hudi do for that? So Hudi has this pluggable index layer. Uh, each record get any record that gets written into Hudi will be tagged with the location info, essentially where under what storage partition it's going to get stored and what's the under what file group it's going to get stored. And this whole data set is organized as a tree style file layout, as we saw in the previous slides. And I'm saying tree style. I think I did not bring it up then. Those file slices and file groups are again sorted by time. And Hudi can quickly jump to a particular, when you do a snapshot query or a time travel query as of certain time, Hudi can quickly jump to a particular. So think of it like a tree map kind of thing, and it becomes very easy to go to a particular instant in time. Um, the invariant is that a record key is routed to a particular file group and it never changes. That record key will always be within that file group. Even the updates for that record will go to a log file which will be under that file group. So that is the invariant that we maintain throughout Hudi. And what Hudi does is that it is able to bin pack records while writing itself. So it sees that, okay, let's say you have configured that you want your small file limit to be 128 MB. Hudi will see that can we pack more records into this particular file group? If so, yeah, so go ahead. Do not create a new file group, route it to the same file group, any new incoming record. Um, that deals with the small file handling, automatic small file handling. But there is one caveat when so index lookup is key, right? Index lookup during the write path, we need to be able to locate where the record was. Typically, we use Bloom filter index to locate the records, and it is still a very popular choice. But there are certain challenges when with Bloom filter, especially when you have possibility of false positives and then you fall back to scanning. So in Hudi Flink integration, we solved it differently. This index layer avoids any redundant scan. So what we do here is, instead of Bloom filter, using Bloom filter, we restore the mappings, the record key and the file group mappings in Flink's state backend, which then serves as storage for all the Flink operators that we have. So the state backend, the advantages of that are that it's very, very performant, and there is no chance of false positives because you're storing the mapping directly, right? It's no more a Bloom filter. And then all the operators can utilize that. The state backend can be persisted, and all the operators can utilize that. So how does it look like when streaming data is ingested? So what Flink will do, it will first convert, and by Flink I mean Flink Hudi integration. This is in Hudi. This code is in Hudi repo. So it will first convert the record into Hudi compatible in memory structure called Hudi record, and then there is a bucket assigner operator which receives this Hudi record and checks the state backend to determine whether the incoming record is a new insert or upsert or delete record, and subsequently tags this Hudi record with the location info. Location info is nothing but the storage partition and the file group ID to which this record should be routed. Once that is done, the bucket assigner operator, so this is passed to the bucket assigner after the records are tagged with the location info. it is passed to this stream writer operator. So stream writer operator will buffer the Hudi records and flush them to the disk, which is essentially your Hudi table. And then eventually when the metadata is updated, it will say that your record is committed, and return back that you are done with the write. So this kind of helps us and provide the record key helps in providing exactly one semantics, even if the same record is ingested again. Hudi will dedupe automatically uh, before doing the write. And then in the background, as I mentioned above, we are doing cleaning and compaction, so that older versions are cleaned up. This is configurable. You can prefer to choose to keep let's say 5 older versions and then clean the rest. um, so that was about ingestion. Then about materialization, we preserve all the change that happens. So Hudi has this meta fields associated with each record, and one of the key meta fields is underscore Hudi underscore operation, which will basically tell you what change happened on that record, whether it's an insert, it's an update, it's a delete. And Hudi uh, automatically does event time sequencing while creating your Hudi table. Apart from the key field, we also ask you for a pre-combined field, and based on the pre-combined field, Hudi is able to preserve the ordering. um, so that way it the snapshot view can be queried by all kinds of engines, and Hudi can do time travel. Uh, Hudi is able to emit CDC records for the table that is happening on the Hudi table itself. So you can build a CDC stream out of Hudi table, and we'll see how that helps in incremental ETL. So incremental ETL, as I talked about the medallion architecture in the beginning, that's where it is most helpful. And now with the understanding of Hudi timeline and the file layout, it will be much more clear. So Hudi has a rich set of file system view APIs, which again use the commit metadata that is available with the timeline, and it can exactly tell you what changed happened between any two commits. And in the downstream pipeline, you can just apply those changes. So that's how you don't have to recompute anything. You just apply those changes, and you build, let's say, two-step incremental ETL pipeline. But that all works like a charm when in the happy path. But what happens? How does Hudi automatically recover if there is a failure? Like most message logging systems, Hudi maintains checkpointing. So the thing to note here is that the incremental dataset info are abstracted into splits for most of these engines, right? Presto, Trino have notion of splits, even Flink has notion of splits. The streaming reader does this bookkeeping of offset for each split it has consumed. Once the reader task recovers, it would continue with the offset from the last successful checkpoint. And you can also reset to a specific, let's say, another use case where you figured out that you consumed bad data and you wanted to move back. So you can actually set the offset to earliest, much like Kafka checkpointing mechanism. And then you can consume the full data set if you want. So we saw how Hudi Flink integration kind of unlocks the incremental ETL capabilities and helps in building medallion architecture. The main thing out of this is that Hudi table is that persistence layer for the Flink dynamic tables, and changes can be applied incrementally. This is what a Hudi stack looks on cloud. I won't bore you with this diagram. The key thing here is that the Hudi box, where it offers not just ACID guarantees but managed table services and multimodal indexes. How does it work with the query side? So this is Presto, but it's very similar to Trino, as Presto Trino are similar in some sense. So what happens on a very high level, Presto is also a distributed MPP style architecture. You have a coordinator which acts like a brain of the system, and it will do query parsing. It will figure out what splits are needed and then distribute the work to different workers. The Hudi connector in Presto, what it will do is, first, the metadata of the Hudi table needs to be synced to some catalog. In this case, it's Hive Metastore. And then Hudi connector will use some indexes in the metadata table that we saw earlier. The split manager in the Hudi connector will use those to scan, to figure out what needs to be scanned. So if we look at what happens behind the scenes when you're executing a query, the very first steps to build the splits, you need to fetch the metadata, right? That is followed by what all stages will your query have and how to distribute the workload. But fetching that metadata is very key to improving your query performance. If you're not doing that efficiently, your whole query plan go wrong, and you might be scanning a lot more data than needed. So Hudi has this multimodal indexing subsystem where it will maintain different indexes such as files, column stats, Bloom filters, record level secondary indexes, and you can even build these indexes concurrently. Whenever a query comes in, so let me take an example of files and column stats, how it works. Basically, when a query comes in, we'll look at the files index, figure out based on predicates what partitions can be pruned. Then among the remaining partitions, and if the query, I'm assuming you're not doing select star from table. That's it. That's not your query. You have some predicates, right? And you have built column stats on the column contained in the predicate. Then it will use the column stats to skip the data within the files obtained after pruning the partitions. So kind of like aggregated indexes. This is the architecture for the Hudi connectors. As I talked about earlier, split manager passes the predicates. There's a terminology, tuple domain is a terminology from Presto Trino, but essentially it's a bunch of predicates to the file skipping manager, and then which will then call the metadata reader and figure out based on the predicate exactly what files need to be scanned. We did some benchmarking with the GitHub archive dataset. On the PR that we see here, this is still not merged to master. But on the PR, there is a benchmark with SSB dataset as well. So that shows the query time and total amount of bytes scanned with no layout, and if you have clustered your data in linear order or in z order fashion, if you have built column stats, how does querying become so much faster, right? um, so I don't think I can play the demo here. I'm already above 35 minutes. I'll quickly talk about, pause this. I'll quickly talk about the roadmap and the community a little bit. Uh, in our roadmap, we want to have first-class support for CDC data, that is, support incremental queries across all query engines. Today, we can only support snapshot and read-only view queries in Presto Trino. But in Spark and Flink, we have support for incremental queries, and we are extending that support to other engines. Then we are going to add more things to our secondary indexes. So anybody familiar with Postgres must have heard about indexes on expressions. Many database systems have it. So you can build indexes on functions of column. So that unlocks a whole new set of capabilities and helps to decouple partitioning from table level to get it to the storage level. This link points to the RFC about what we are going to do there. And then we are, of course, going to have some new table and merge API so that it's much easier to integrate with engines. Over time, we have realized that our APIs still need some work so that it's easier for users to integrate Hudi. We are also working on adding features such as multi-table transactions so that you can atomically commit changes across multiple tables. This RFC talks about the roadmap in much more detail, what all exciting features, including what we plan to do for vector data, indexes for vectors. You can read this RFC at your leisure, and I hope you can also contribute. If you love databases, then please contribute to Hudi as well. We have seen phenomenal growth since 2020s. Even the Hudi project originated at Uber in late 2016, it has picked up steam a lot in the last couple of years. We have 400 plus active contributors. To engage with our community, if you like Hudi, please give us a star, and you can join us on Hudi Slack, and we do weekly office hours. You can find the link to that in the Hudi official website. That's it. Yeah, we can now take up questions.
Yes,
Thank you.
many thanks, Sagar. Great presentations.
Yeah, sorry, I went a little bit over time,
No, that's
but I
perfectly
wanted to
fine.
go into a little bit of detail. Yeah.
No, that's perfectly fine. I think everybody's enjoying. So we have few questions. If you can both take a look at those and see who wants to answer. So the first one, yeah, go ahead. Both Shirley and Sagar.
Could the
How do you
Hudi-based Presto
support?
support serving? Okay. Could the Hudi-based Presto support serving processing use cases with high QPS? Um, of course it can, but you have to be a little bit more specific here about what do you mean by high QPS. As in, uh, so it depends on uh, um, whether you are running Presto on just single node, uh, or you have a big Presto cluster and concurrent queries running. But we have benchmarked Presto Hudi connector, which is on par with Presto Hive connector for TPCDS dataset. And the same set of configuration. I think it was 12 worker nodes, R5, R5 4x large instances on EC2. Um, and they both, the main thing is that Hive and Hudi connector are on par. So I'm not sure if I answer your question precisely, but if you yeah, I can chat offline and understand more about your use case. What do you mean by high QPS there?
Okay. Okay, so Shirley, get ready. This one is for you. Can Doris
Yes.
run Kubernetes?
And for the first one, can Doris run on Kubernetes? And the answer is yes, it supports running on Kubernetes. And we have a Kubernetes Doris operator. It is for you to smoothen your deployment and maintenance on Kubernetes environments. And then the second question, it's about will it be hard to scale the front end and back end nodes? And is it as simple as adding a machine? And yes, pretty much it. And let me just add more information about the front end and back end nodes. Like the front end nodes works in a few aspects. It is responsible for cluster management and kind of like the name node of Zookeeper and Hadoop. And also it's also responsible for metadata storage, and it can access and process requests from the users, and it's very easy to scale. And then the backend nodes, they are responsible for storage of the data and computation of data. Like I mentioned, it can do query execution, and you can scale the backend nodes online with one simple command. and during the scaling process, it will not interrupt the running of your online business or services. So that's it.
Thank you. And there is one
Quick
more.
question tangential to what Shirley said. Uh, so I remember during the talk you mentioned something about compute nodes being stateless. Uh, and just now you mentioned if you talked about if it fails, it does not affect the queries. So uh, in that scenario, since the compute is stateless, I'm assuming you are going to uh, in order to serve that query, you are going to start the work again right from the beginning and not saving anything, any part of the. So let's say a query is split into certain number of stages. You're not really saving the results of a particular stage anywhere. Is my understanding correct?
Well, so you want to know more about how the compute nodes work? And it's actually part of our storage compute separation plan, but it's not a very ultimate one. And as I mentioned, it's different from what our usual normal backend nodes do. Is that it do not store any data, so it's like it's wandering. So during peak times it will join and do the computation, and other times it
Yeah.
will. And for some other workloads, it will be prioritized to be deployed or assigned to the compute nodes. And if you need more information,
Okay.
I will do some work after, because I want to enable the most intuitive and simple to understand way for you. And I have your email, and I can send you some documentations or demonstrations later. And when this webinar video is uploaded online, I will also paste it on the comment section. So
Oh,
it's
that would
more
be great.
informative.
Yeah, yeah, yeah. Thank you. Thank you.
Thank you. And can we just like address the last question? Any plans of having hidden partitioning or partition evolution like as iceberg?
Um, I'm assuming that is meant for Hudi, since it's comparing to iceberg. Uh, so it's so this question actually cuts deeper. Uh, uh, if you think about, and it's related to the functional index that I mentioned during the roadmap discussion. Um, so partition evolution, right? First of all, partition. What's the real use case for partition evolution? Let's say you have partitioned your data horribly, and then you realize later on that okay, your query sucks right now, and you want to improve your partitioning from uh, I don't know, maybe you are partitioning data previously on a monthly basis, and then you started partitioning to improve your query performance on a daily basis, right? uh, you don't want to rewrite the old data and still want to support with the two types of partitions, evolve the partitions to improve your storage layout. That's the main use case for partition evolution, so that your queries don't affect it. The same goal can be achieved with functional indexes. Suppose you build an index on date string of a timestamp column. You have a timestamp epoch value, and you are building an index called date str on that. And the index will tell you, okay, for the evaluated value of dates str timestamp column, what exactly are the collection of files that contain this date str value. Then it doesn't really matter how your data is partitioned, right? Partitions, yes, partitions should have two benefits: partition pruning and a convenient way of organizing your data. Um, but at the end of the day, if through the index itself you can serve those queries faster, and at the same time decouple how your storage partitions are from the table partitions. And what I mean by that, your physically your partitions could be anywhere, logically your partitions could be something else, some function of some column that could be a logical partition. So that those things can be achieved with functional indexes, and databases actually do those things. Uh, now coming to your question, any plans of having hidden partitioning or partition evolution? Yes, and functional indexes will cover that. I have this particular use case in that RFC. I am the author of that RFC, and in the slide deck I have included the link. If you want a quick thing, I can bring here in the chat. But to answer, yes, we'll be supporting that in 1.0 version.
Yes, do please, like we don't have more time today, but if you have any resources, please do share it in the chat or email me and they will be sent to all participants. And we're really out of time, unless somebody have another question, and I think we have answered everything. Many thanks again, Shirley and Sagar. This was really super insightful, super interesting. So thank you once again, and hope we'll see you soon again.
Yeah, thanks
thank you
the
for
opportunity.
building
Love
this space for us.
Thank you all participants. See you soon at next Serverless Tribe webinar. Bye.
Bye.
Bye-bye.